Hello, I am Geneva Bowling and this is my lab about projectile motion. The purpose of this experiment is to track and analyze the trajectory and the velocity of the paper ball thrown in the air at an angle. The observed path of the object will then be compared to two computational models that will predict the trajectory of the gravity and drag force on the object. The fundamental principles that we use is Newton's second law, force of drag or air resistance, force of gravity, and the kinematics formula. We originally predicted that adding drag would make our model more accurate, however, because our ball was thrown at a low speed, air resistance was negligible, meaning gravity-only model actually fit our data better, and we will see in a second. For our experiment, the system is the paper ball, and the surrounding is gravity and drag. Our initial conditions are mass is equal to 0.0045 kilograms, and diameter is 0.06 meters. We find our initial position through a tracker, and same goes with initial velocity. Possible sources of error: the paper ball is not perfectly round, and human error from tracking. Before we can start with our glow script, we have to find initial velocity for both x and the y components, and we have to use the kinematics formula to determine that. For our predicted model without drag, we set our initial conditions. Drag constant is 0 for this case, and F net is only gravity. We also added position and velocity formula to see how far the ball has landed. You can see these changes on the highlighted areas. As you can see, the blue arrow is gravity, the purple arrow is velocity, and our trajectory is a parabola. For our predicted model with drag, everything is the same except our drag constant, which is set at 0.500. You'll see why we set it at 0.500. I also add changes at the bottom of the code so you can see how the force of drag impacted our paper ball. In this model, you can now see the force of drag, which is pointing the opposite direction of velocity since it is friction in air. Also, our trajectory has changed slightly. The experimental data is the blue dotted line, the predicted without drag is the orange, and the predicted with drag is green. The experimental model is actually closer to the predicted model without drag compared to the model accounted for drag. This is probably because the paper ball is thrown at a small initial velocity over a short amount of time, so air resistance is negligible in this case. However, they both share the same trajectory shape and the start position. The only difference is their F net. One is accounted for gravity and drag, and the other one is only for gravity. Do any of your models predicted a terminal velocity? No, terminal velocity was required to have the same downward force of gravity in order for the object to stop accelerating. To actually find it, a new experiment must be made. For example, a paper ball falling vertically from a multi-story building. Imagine if the object were initially thrown straight up with the same initial speed as in your experiment. Would the time this object take to reach from the ground be the same, longer, or shorter than the time it took in your original experiment? The time to reach from the ground would take longer because using the kinematics equation, a higher y component of the initial velocity means it would increase the time on air. Think of it this way: if the x component is 0 and the y component must be larger, and a larger initial y component of velocity would make a higher final upward velocity, which means the ball climbs much higher and takes a longer time to rise, which also means a longer total time in the air.